Okay, so to finish off what we were doing the last time, I was saying that this is where we're stating the relevant bit of the central limit theorem. Then we make a comment about the distributions that we've got. Probably should be green. And then finally we draw a conclusion from that, which is that final bit there. Okay, so moving on. This is a question about batteries. So Dale has an MP3 player that uses one AAA battery. When a certain brand of AAA is used, playing time varies according to the distribution, with a mean of 10.85 and a standard deviation of 1.35. So they're sold in packets containing different numbers, and Dale buys a packet containing N, and each battery is used in the MP3 player until it's exhausted. So let X bar N denote the average playing time per battery for a packet of N batteries. So basically this is our distribution where our sample size is N, and it's a distribution which has the mean playing time of every battery. So it's a mean time playing of each battery, and we have a sample size of N. So the two histograms below represent the distribution of when the sample size is 4, and here it's when the sample size is 15. So which histogram illustrates the distribution of X bar 4? Explain your answer. So again, we say that the CLT, central limit theorem, states as N increases, the approximation to normality improves, and sigma of X bar decreases. We saw that last time. So then we say histogram B has a smaller standard deviation and a smaller right hand tail than histogram A. Hence, this implies that histogram A illustrates the distribution for X bar 4. So again, we've followed the same method. I'll just fix up the fact that I can't spell histogram and I can't spell the deviation. It's not so good when you're a year 12 math studies teacher, but anyway, so we've stated what the central limit theorem says here. We've then made a comment about our histograms here, and then we've drawn a conclusion in the final sentence there. So according to the central limit theorem, the distribution of the sample means of size N will be approximately normal if N is sufficiently large. So they ask if N equals 20 is sufficiently large in this case. Explain your answer referring to part A as appropriate. Well, if we have a look in part A, what we've done is we've established that histogram B is the standard deviation for X bar 15. So from A, we notice that the histogram for X bar 15 is symmetric. We also know that as N increases, the normality of X bar N improves. This implies that n equals 20 is sufficiently large to ensure that the distribution of the sample means will be approximately normal. So in this case I've done it in a slightly different order to what we're used to, but this is the comment about the central limit theorem. This is, I guess, when we're talking about the histogram, and then this is the conclusion that we draw. So that's how we answer that one. So we need to show that x bar has a mean of 10.85 hours and a standard deviation of 0.302 hours. So this is just a basic application of the central limit theorem. So we know that mu of x bar for 20 is going to be equal to mu, where that's the population mean, which is equal to simply just 10.85. So we've already done that one. Standard deviation, sigma of x bar 20 is equal to sigma, where sigma is the population standard deviation divided by the square root of 20, so 20 is our sample size in this case, which is equal to, now if I just need to remind myself, our population standard deviation is 1.35 on the square root of 20. And sorry, I'll just fix up the formatting, that always messes me up when I try to do fractions. So then that's just simply equal to 0.302. Okay, so that's just a basic application of the central limit theorem. So now they want us to use that, so we want to find the probability of a particular sample of 20 being greater, having a mean greater than or equal to 10. So that's just use of the NCD function again. So our lower limit is 10, our upper limit is 1 times 10 to the power of 99, because that includes all the area right to basically infinity on the calculator. Then we put in our standard deviation, which is 0.302, and then our mean, which is 10.85. Possibly what I would do in this case is, to get better accuracy, I would find the standard deviation to 4 significant figures and use that in this calculation. And so then that equals 0.998. So that's our probability. So our probability is going to be 99.8% that the mean life of a sample of 20 is going to be greater than 10 hours. So that's pretty good. That's a pretty good probability, really. Okay. So moving on. When a normal distribution is used to approximate the distribution x bar 4, which we saw here, so that's that histogram A, then the probability of a particular sample of 4 having a mean greater than 12.5 is that value there. So is 0.0725 too small, too large, or about right in comparison with the exact value of the probability? Explain your answer referring to the histogram of x bar 4. So if we notice here that histogram A is definitely skewed to the right, so there's definitely going to be more area under this, so 12.5 is about there. So this section of the histogram here is going to have more area than if this was a normal distribution, because a normal distribution would come down a lot closer and would be virtually 0 by the time you get to 12.5. So pretty much it's going to be too small because we're using a normal distribution to find this value, but on our distribution in histogram A we actually have more area, so this is going to be too small. So to formalize how we'd say that, if x bar 4 is skewed to the right and a normal distribution is symmetrical, then probability of x bar 4 being greater than or equal to 12.5 being approximately equal to 0.00725 would be too small. There will be more area in this tail of the skewed distribution than in the tail of the symmetrical distribution, or the symmetrical normal distribution. Might want to put there. Okay, so that's sort of an interesting question, but that's how you would answer it. So just being nice and explicit in your answers. Okay, so we want to move on. So this is where we get to the kind of the meaty end of this problem. So Dale's going on a long driving holiday. So he decides to take enough batteries to give a probability of 90% or greater of being able to use his MP3 player for more than 200 hours. So show that 18 batteries will not be enough. So we start by thinking, well, what mean do we need for 18 batteries to last exactly 200 hours? So if 18 batteries lasts exactly 200 hours, then we need the mean of the sample of 18 to be simply 200 divided by 18, which is equal to 11.11.11 hours. This is a good example actually of where you use 4 significant figures for your calculations before dropping back down to 3 to give your final answer. So the distribution that we're working with is x bar 18, and by the central limit theorem that's normally distributed with a mean of 10.85 and simply a standard deviation of 1.35 on the divided by the square root of 18. And again, I've made that mistake with the decimal, but I know that you're a very forgiving class, so that'll be okay. So we want to know the probability of the total time being greater than or equal to 200. So that's going to be equal to the probability that a particular sample of 18 batteries has a mean greater than or equal to 11.11. And so we again use the NCD function. So that's the lower value is 11.11, the upper value is 1 times 10 to the power of 99. The standard deviation is 1.35 on the square root of 18. Still didn't get the brackets right. And the mean is going to be 10.85.